Okay. We will go on with our videos in the grade 11 statistics and probability classes. Remember that in the last video we have defined that a sample space which has a finite or countably infinite number of outcomes is said to be discrete. We have examples shown in the previous videos and the solution also. On the other hand, the sample space which has an infinite number of outcomes yet uncountable is what we call a continuous sample space. Now, what I have talked about in the last video is that in this video we will talk about a subspace, or rather a subset of a sample space. So that is what we call an event. Okay, now for most experiments we're not actually interested in the entire sample space. Okay, rather we only need to know a subset of it, a part of it, a very important part of it. It depends on our point of view, depends on our question, on our problem, but most of the case we only need a part of it, not the whole sample space itself. So let's have this definition number 3. We will call a subset A, okay, of a sample space big S of an experiment is called an event, usually denoted by a capital letter except S. So a subset A is what we call an event. So we call it event A, event B, event C, whatever is the the notion is it's a capital letter except S, because big S already takes the um the the sample space. So let's have more examples. Example 2, if we roll a die and observe the number of a number that comes up, two possible events that can be defined are, for instance, we can get the outcome which is odd and the outcome which is even. So imagine yourself, if we're going to toss a die, so we have 1, 2, 3, 4, 5, 6. We're just going to take all the outcomes which are odd for letter A, and we will define that as in our answer. And for our B, let's define it as our answer here, which is the even. So we can say, since we call this event A, we will write it something like this. So event A is equal to the numbers 1, 3, 5, which corresponds to the odd outcomes in a possible roll of die. And B, event B, will call this event B equals 2, 4, 6, which are the even numbers when we roll a single die. So this is how we write events. Okay, similar in how we write the sample space, only that the sample space we write it with big S, and we write all the possible outcomes there. All the possible outcomes. Moving on, let's have more examples. Imagine rolling a die and observe the number that comes up. Similar with the previous one, consider the events C and D. Okay, so for letter C, what we're looking at here is that the outcome is at least 7. So when you say at least 7, it should start with 7 and then going up, right? So that's the word at least starts with, should be that or more than. So remember that when we roll a die, we only have outcomes like 1, 2, 3, 4, 5, 6. And when we start with 7, we do not have an outcome which starts with 7, or rather, 7 and above. So meaning this event C is what we call an event which cannot be done. Okay, an event that cannot be done, since the outcomes are there's no outcomes, right? So we call this an impossible event. Okay, an impossible event. So we denote impossible events to have this empty sets with them. So we call that event C is equal to an empty set, which denotes that event C is an impossible event. It cannot happen. Okay, for event D, the outcome is either odd or even. Okay, event D is that outcome is um either odd or even. So we get all our answers from event A. Remember event A to be outcomes which are odd, and event B which are the outcomes which are even. So we combine them in a single set. So what we have are actually the set what the event D is equal to 1, 2, 3, 4, 5, 6. Okay, and remember 1, 2, 3, 4, 5, 6. Event D, this is just equal to your sample space, right? So event D is equal to 1, 2, 3, 4, 5, 6, which is equal to your sample space. Meaning to say that event D, whatever happens, event D always is the one which is happening. Whatever experiment you do, whenever you roll a die, it's really sure that D is happening. So that's why what we call here with event D, we call this as a sure event, a certain event that it's really going to happen. Whatever will do. That's why in some books they denote this big S here, the sample space, to be sure. That is, it's a sure event. Okay, hopefully you got that there. So we have C is an impossible event denoted by our empty set here. Rather, sorry, that's event C. Sorry, C is an empty set that is an impossible event, and event D is a sure event which is equal to your sample space, which has all the possible outcomes of whatever experiment you have. And then with these events, we can actually do some operations with that event. Okay, so as events are simply subsets of sample space big S, we can perform set operations on one or more events here. So let's define, let A and B be two events defined over as the same sample space big S. Then we have this operations with events. Okay, so first, this may come familiar when you already have your set theory class, or even at least your set theory and logic class. So we have here the intersection of A and B, denoted by this A cap B, or we can read this as A intersection B. Okay, A intersection B is the event whose outcomes belong to both. Okay, take note, both A and B. How do we present this in a Venn diagram? So we should know how to present this in a Venn diagram in order for us to clearly understand it. Now, Venn diagrams are created by John Venn in the 1800s. So this is what that Venn diagram looks like. So we have this rectangle which represents our sample space. Circle, this first circle here is event A, the second circle here is event B, and notice the red shaded part. That is their intersection, in which the outcomes belong to both A and B. Okay, outcomes that belongs to both A and B. Take note, it's possible that there's no outcome that belongs to both A and B. We will call that mutually exclusive events. And here we will call this non-mutually exclusive events because there exists some things that which are common to them. We'll get to that soon. Next is the union. The union of A and B, denoted by A cup B or A union B in short, is or in general, is the event of all outcomes in A or B inclusively. Okay, including A and B. A or B, including A and B themselves. Notice the operation, the the symbols of the operations is like the reverse one. The intersection is A like this. It's like a reverse U, and the union is like the correct U. So we have A intersection B, A and A union B. So what does this look like in the Venn diagram? It looks like this. All is taken in consideration. Um, we have here the shaded part of A. All of the A is shaded, and all of the B in the shade is shaded, including their intersection is also shaded. Now going back to mutually exclusive events, we have here in the last bullet, if A intersection B has no common event, has no common outcomes, that is, their intersection is empty. Okay, if their intersection is empty, then the events A and B are said to be mutually exclusive. So this is just like this. They do not have something in common. Therefore, their intersection is empty. There's no outcome that is common to them. So we call this mutually exclusive events. Here in the first Venn diagram, we call this non-mutually exclusive events because they have something in common. Okay, hopefully you got the gist of that, and you may take a screenshot whenever you want. Okay, so that you'll have a copy of this. Next, we can also take the complement of event A. So let's have that definition number 5, the complementation. Let event A be defined on the same sample space big S. The complement of A is denoted by A prime. In calculus, we call this A prime or A complement. But here in this context, in set theory and in probability, we'll call this A complement. All right, not A prime. Okay, A complement is a set of outcomes in big S, not in event A. So what do we mean by that? The set of outcomes in big S, not in A. So this is what we call the A complement. So if this is big S and this is our event A complement is everything outside this A. Okay, we denote that as A complement. Either of this. It depends on your book. Usually we use this one. We read this as A complement. Okay? Okay, more on operation with events. Let's have one example. Okay, we call this example 4. Consider the experiment of tossing two fair coins, and we will be defining the events. A, two heads come up, and B, two tails come up. Okay, we're tossing two fair coins, and then event A means two heads come up, event B means two tails come up. And we'll be finding the union, intersection, determine if they are mutually exclusive, and find the complement of A. So I'll leave this to you as an exercise. Maybe you can pause the video for that, and I'll ready the solutions on the next video for this. Okay, so I think it's due time to end here. Thank you very much for watching. Hope you'd like and subscribe, and keep in touch. Be updated. We'll continue this batch of videos here in statistics and probability for grade 11. So thank you very much for watching.